Okay, so good morning, everyone. Thank you very much for your invitation. I am Martina Pastorino. I am an assistant professor from the University of Genoa in Italy, and I'm going to talk about probabilistic graphical models and deep learning for remote sensing image analysis. This was the topic of my PhD that I carried out at the University of Genoa in collaboration with INRIA, Université Côte d'Azur in France. And previously, I was a student in telecommunication engineering in a master at IMT Atlantique in France and at the University of Genoa. So I carried out my research mainly in between Italy and France. I will deactivate my video camera now because the network is not that strong, so I'd rather not have it jump on and off. Sorry. Okay.
That's okay, no worries. No worries.
Thank you. Okay, so okay, perfect. This is the outline of my presentation after giving an introduction and motivation for the combination of PGMs and deep learning models. I will present briefly different kind of integrations, focusing mostly on a specific one, and then I will show some relative examples in the field of remote sensing, specifically classification of multimission SAR images and a multi-resolution fusion framework for satellite and drone imagery. And finally, I will draw some conclusions. So we can start from the introduction. As you all very well know, remote sensing for Earth observation is this process of detecting and monitoring the characteristics of a portion of the Earth's surface by measuring emitted, reflected, or backscattered radiation with sensor at a distance, which are typically from satellite, aircraft, or drones. So in this framework, semantic segmentation plays a primary role because it can allow for the analysis of land cover mapping, which can have application to urban sprawl, precision agriculture, forest inventory, natural disaster management, glacier monitoring, climate change monitoring, etc., etc. And as you all very well know as well, deep learning techniques are currently state-of-the-art for semantic segmentation tasks. They achieve very high per pixel accuracies, and they can also efficiently reproduce the shapes of the objects segmented. And among the most successful architectures, we have mainly CNN-based, convolutional neural network-based architectures, for example, fully convolutional networks, and vision transformers. However, despite the success of these deep learning models, we still have several challenges, especially in the context of remote sensing. The two main challenges are pictured in this slide. First of all, we often deal with multi-sensor and multi-resolution data, meaning that images come from different sources with different scales and characteristics. And for example, at fine scale, we get precise details, but also more noise. And at coarser scale, we get more robust information, but we lose detail. And the challenge is to effectively fuse this information for land cover mapping applications. And secondly, there's often a lack of ground truth data for remote sensing applications because creating ground truth map is expensive and time consuming. So it's very rare to have spatially exhaustive ground truth maps like we find in benchmark datasets. And we usually have something with composed by isolated patches that usually affect the performances of supervised deep learning methods. So these challenges motivate the need for more advanced modeling approaches. And this brings us to probabilistic graphical models. Probabilistic graphical models are approaches to structure prediction. It means that you are going to predict outputs characterized by some dependency structures. For example, neighboring pixels in an image. So in probabilistic graphical models, you represent variables as nodes in a graph and then model the relationship between these nodes using probability distributions. So we can have different kind of graphs, for planar, multi-layer, bipartite, irregular, to express different dependencies depending on the input data we have or the problem we want to model. And then we have these probability distributions among the nodes in the graph, which are typically Markovian. And we have some Bayesian decision rules. We can have probabilistic graphical models on directed acyclic graphs, and this is called a Bayesian network, or we can have probabilistic graphical models on undirected graphs, for example, Markov random fields. And depending on the graph topology we choose, we can model spatial or multiscale information, or both. These are two examples of different graph structures representing different dependency structures. So on the left, we have hierarchical probabilistic graphical models on quad tree. What's a quad tree? It's basically a pyramidal tree in which each layer is double the previous one. So it's a regular pyramidal tree. The graph in this case is this pyramid, and we can model multi-resolution and multi-scale relationships. We have Markovianity across scales with this formula. So basically, we know that the probability of having a certain pixel label is given by the probability of having a certain pixel label in the parent node. But this kind of model does not allow for the introduction of spatial information. It doesn't model spatial information at each scale, only multi-scale information. And then on the right, we have a planar Markov mesh. In this case, our graph is our planar pixel lattice, so our image lattice, and the model accounts for spatial information. We have Markovianity in space with a causal model, and it's basically an extension of Markov chains to two-dimensional lattices. We have our other classical models, our classical examples of PGMs here. For example, a classical planar Markov random field in which our graph is again a planar pixel lattice and it models spatial information. In this case, with respect to the Markov mesh, we have a non-causal model because we can account for interactions between neighboring pixels that are before or after the pixel we're considering. And basically, what we are handling with this MRF is the probability of having a certain class label. So the joint distribution of all labels is defined by the Hammersley-Clifford theorem. So basically, the energy of our MRF is given by a unary potential, which represent individual pixel predictions. And by pixel predictions, I mean the label we want to give to a certain pixel. And then pairwise potentials, which enforce smoothness between neighboring pixels. Basically, a probability that given a certain class label at the pixel, we will have the same class label at the neighboring pixel, which is typically true in natural images. And then we can have higher order potentials. Usually, most of the models stop at the pairwise, but it is possible to account for higher order interactions. So in all these cases, the PGM is the model for the prior probability, so the probability of having the class label. And then when we want to perform Bayesian classification, we pair this model with some likelihood, so the probability of having a certain observation given the class label, so the conditional independence, and then some decision rule, for example, maximum a posteriori, maximum likelihood, whatever we choose for our problem. Finally, the last model I am going to introduce in this broad presentation of PGMs for remote sensing are planar conditional random field. So basically, again, the graph is a planar pixel lattice. We model spatial information. And the only difference between the CRF and an MRF is that we are extending Markov random fields by allowing to incorporate feature vectors, thus providing more flexibility. So basically, the model here is not on the prior, but it's on the posterior probability. We are modeling the probability of having a certain class label given our observation. Okay, so we can include feature vectors in our computations and in our posterior probability evaluation. Let's have a very brief look at the state of the art about the combination of deep learning and PGMs. Most of the time, PGMs are used as post-processing steps, so we can use them to refine the classification results obtained by neural networks. They have been used to combine probabilistic predictions obtained by different sources. For example, we have predictions by neural networks and then by probabilistic classifiers, and the SCRF can be used to combine these different models output. And they have also been used in pre-processing in a semi-supervised manner to simulate ground truth for the training of CNN. But actually, we can have several possible combinations of these two families of approaches. So we can have a cascade integration where one method is applied after the other. Usually PGMs are used in post-processing, as I just said. We can have a topological integration, which tries to exploit the common topology between neural networks and PGMs. And then we can have end-to-end integration, where a single model is trained end-to-end with some equivalence theorems between the two approaches. In this presentation, I will mainly focus on the second part. So we're going to discuss topological integration of probabilistic models and deep learning. So what's the common ground with the main idea for this topological integration is that convolutional networks involve several multiscale processing stages through the convolutional layers and the pooling layers. And this perfectly matches the graph topology of a hierarchical probabilistic graphical models that can exploit multi-resolution and spatial information. This is the key idea of the methodology. We can exploit this intrinsically multiscale architecture of fully convolutional networks through a quad-tree topology. So we extract the activations at different layers of the neural network, which correspond to different resolutions, and then this naturally fits a quad-tree topology. We can define a hierarchical PGM on this quad-tree in order to mitigate the impact of multi-source data or sparse ground truth data, because with this methodology, we are both modeling interlayer and intralayer interactions, so multi-scale information if we have multi-resolution data, and spatial information if we have scarce ground truth. So we are enforcing some relationships between neighboring pixels. And we can use some ensemble learning techniques to link the representation extracted by the fully convolutional network and the Bayesian structure of probabilistic graphical models. So basically, the idea is that you can use ensemble learning to transform the activation extracted by the neural network into posterior probabilities that can fit the quad-tree, the PGM requirements. So in order to model both multi-resolution and spatial information, we can have Markovianity across scales and in space. So what we do is a combination between a hierarchical MRF and the Markov mesh, and which is represented by this formula. We have some probability that a pixel has a certain class label given the neighboring one, and we have the same probability of this pixel having a certain class label given the class label of the parent pixel, so multi-resolution and spatial information. And this model happens to be causal because it's demonstrated by the theorem 1. So the joint distribution of all labels and feature vectors in this quad-tree is entirely defined by parent-child transition probabilities, past-neighbor transition probabilities, and the pixel-wise data conditional likelihood. Everything is causal, and we can use marginal posterior mode criterion for inference, which can be expressed in closed form equation, 3 recursive closed form equation, because this model is causal. So it's not iterative, it's just 3 equations to apply recursively. Why are we using a marginal posterior mode instead of a maximum a posteriori in this case? The idea is that the concept for inference is the same, but this criterion gives a cost depending at which resolution it happened. So it's it's more practical with respect to maximum a posteriori for multi-resolution problems, because, you know, getting a pixel wrong at coarse resolution has a different cost than getting a pixel wrong at fine resolution, because it affects a greater space in an image. Okay, so I'm moving to some examples of methodologies with some experimental results. So the first methodology involves the classification of Multimission SAR images. So thanks to the current advances in space missions for Earth observation, we have access to multimodal satellite imagery, for example, characterized by different SAR modalities. And you know better than me that different SAR modalities means different frequencies, bands, polarization, and spatial resolutions. And these different characteristics influences the way the electromagnetic wave emitted by these active sensors interacts with the surface of interest beneath. So it means that through this acquisition, we have complementary information. So it may be interesting to combine these different acquisitions to exploit all the information we can. So the idea of the method is the same that I presented before. We have a fully convolutional network. In this case, it's a UNet. We train it with input multimodal information. Since we have data at multi-resolution, we insert them in the neural network at the right resolution. So we insert the finest at the first input layer, and then the resolution R1, which in this case is twice coarser, is inserted after a pooling layer. And then we extract this activation and we create our hierarchical PGM. One in-between step in this methodology was multi-mission image registration, because of course, as you all know, when you obtain images from different sensors, you also need to align them, because most of the time they are not perfectly aligned. So we defined a registration method for large scale images. It was built for optical to SAR image registration, but it can be extended to multimission SAR data, as we did in this case. And basically what's happening in this method is that you define a tiling strategy, because it is applied to large scale images. And then you have a piecewise stationary model to favor computational efficiency, and you apply piecewise rotation scale translation transformation in order to find the right geometry. And we did apply this methodology to this multimission SAR dataset composed by Cosmos SkyMed images, SAOCOM, and Sentinel-1. They come from different space agencies. Cosmos SkyMed is from the Italian Space Agency, SAOCOM comes from the Argentinian Space Agency, and Sentinel-1 is from the European Space Agency. They are different kind of sensors, different kind of bands. We have X, L, and C, different kind of pixel spacing, 2.5 meters for Cosmos SkyMed, 9 for SAOCOM, and 10 for Sentinel-1, and different polarizations. And we had the ground truth information coming from a land cover and land use archive from the region that we were considering, which was Lombardy in northern Italy. So what we did was multi-look the Cosmos SkyMed images at 5 meters, and then multi-look the SAOCOM at 10 to match the Sentinel-1 spatial resolution, pixel spacing. And then they were inserted in the network that I showed you before, going from the Cosmos SkyMed in the first layer, and then SAOCOM and Sentinel in the second layer after pooling. So these are the results obtained on this dataset with our PGM-based method compared with some baseline, for example, the UNet without the PGM, HRNet, which is a network that uses some subnetworks to model multi-resolution information, and then a network with some attention layers. Again, a multi-resolution network with attention layers. And we can see how the modeling of spatial information through the PGM allows for the for better results in the classes that are minoritaries, for example, clutter and water, which is why it then brings to higher overall accuracy matrices. This is because our probabilistic graphical model enforces spatial information other than multi-resolution, so it helps recovering information for the minoritary classes in which we have less samples. And we have an example here showing the results depending on which bands we use for the classification. So we tried only with Cosmos Skymed, Salcom, Sentinel, and then a combination of them. And we can see how actually integrating multi-sensor information allows for better classification results, more precise, and with slightly higher accuracy matrices. Of course, actually, since the classification results was to be obtained at the spatial resolution of the Cosmos Skymed imagery, the X band mainly dominates the results, as we can see in this scatter plot. So even if we use only the X band, we have quite high results, but we have an improvement when we use all the complementary information that these sensors can bring. And the second example is not SAR-based. It's a methodology for modeling burn zones from satellite and UAV imagery. So again, thanks to the current availability of several Earth observation satellites, we have access to data to monitor and map burned areas. In the past, usually what was used was satellite imagery through multispectral channels in the near and short wave infrared wavelength ranges to monitor areas which were burned or burning. But in recent years, unmanned aerial vehicles, or drones, have also been widely used in forest fire monitoring because they are highly flexible, they are low cost, and they have an extremely high spatial resolution. So these two acquisition modes both have their pros and their cons, because drone-based systems, they have a small area coverage, complex scene background, susceptibility to forest cover, which satellites do not have, but at the same time, satellites suffer from aerosol and cloud occlusion, but they give wide coverage and a good revisit time. Instead, a drone needs to be, you need to fly a drone on purpose to check the area. So again, it could be interesting to use both of these acquisitions at the same time. In this case, we have a huge resolution ratio between the two available images, because drone images usually have a resolution of few centimeters and the satellite images of few meters. So we may have resolution mismatch of 1 to 500, 1 to 1000. So basically the methodology that I showed you before was just adapted to fuse this highly mismatched information with a non-regular pyramidal tree. So in this case, our root layer contains the coarse resolution satellite data. The leaf layer contains the fine resolution UAV imagery. And given this spatial resolution, if we were aiming for a standard quad tree, we would need tens of levels in order to maintain the standard power of two relationship, which makes the inference very computationally expensive. So we have this irregular quad tree, and the first layer, the root layer, has many more connections with the second layer. And we can define again a hierarchical Markov random field on this quad tree. What you see in this picture is also are also the methods we use to extract the posterior probabilities. They are different between the UAV and the satellite image, because the UAV had a lot of pixels, so we could use a fully convolutional network, and the satellite imagery, 500 times coarser, did not. So we used decision tree ensemble such as random forest to extract posterior probabilities. So basically, I will not go into details in this slide, but we have this irregular pyramidal tree structure. From layer L to layer 1, we have the same as a normal quad tree. So they are defined with this equation, which is the same that we had before. And between layer 1 and layer 0, we have a fully connected kind of a relationship, which is defined in this in the fourth equation. So this is the data set that we used for this experimental validation. So we have a drone image acquired by INRAE in south of France at 2 centimeter of resolution, acquired shortly after the fire of July 2018. And then we have a Sentinel-2 image at 10 meters of more or less the same date, just 3 days apart. And we took the NDVI and the NIR channels because they are the ones containing information about the dryness of the soil and the near-infrared, the near-infrared wavelengths. And we have ground truth boundaries at 2 centimeters. So in this case, our resolution mismatch is 480, around 500. And these are the results that we obtained with the methodology based on PGMs and deep learning, so which is the third column, compared with UNet, with the deep learning-based fusion based on CNNs, and a recent state-of-the-art method based on CNNs and vision transformers. And what we can see is that the proposed methodology has slightly better performances in terms of false alarm rates. We don't have random spottings in the image like we can see on DBNet. And at the same time, it has the smallest overall error rate because not only it doesn't show high false alarm rate, but it also shows low missed alarm rate. So in order to conclude, I tried with this presentation to show you the primary role of deep learning and probabilistic graphical models for remote sensing image analysis and how we can have some advantages through their integrations within a unique framework, especially because they are applicable to real-world training sets, which is particularly important for remote sensing applications. We have data fusion capability for multimission, multimodal, and multi-resolution images, and we apply these recent proposed techniques for land cover mapping applications, taking into account the specifics of the input typology of our Earth observation data. And the future work may involve the incorporation of semi-supervised approaches because up till now they're mostly supervised. And then some further studies on the mathematical equivalence between CNN-like and PGM-like architectures. So thanks a lot for your attention.